Welcome to section 6.3. Today we're going to be proving that quadrilaterals are parallelograms, and we'll be using some coordinate geometry to help us to prove that quadrilaterals are parallelograms. The definition of a parallelogram is if you show that both pairs of opposite sides of a quadrilateral are parallel, then the quadrilateral is a parallelogram. These are some of the theorems that we've already established in this chapter, but I want to just go over them and make sure we're all on the same page. So Theorem 6.6 tells us that if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. 6.7 tells us that if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Theorem 6.8 tells us that if an angle of a quadrilateral is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. Theorem 6.9 tells us that if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So start to notice that all of these are in if-then form. Okay? So these are conditional statements that are potentially going to have converses in the future. And finally, this would be a new one. If one pair of opposite sides of a quadrilateral are congruent and parallel, then we can determine that the quadrilateral is a parallelogram. Okay, so for practice, I want us to show that this quadrilateral here is a parallelogram. So there's two ways that we can do this. So the first thing we want to do is to prove that this line is congruent to this line. And to do that, we have to use the distance formula. So we know the distance formula is the difference of the x-coordinates squared plus the distance of the y-coordinates squared. Okay, so let's find the distance of CB. So for the x-coordinates, we have negative 2 minus 3 squared plus 6 minus 4 squared. When we solve this out, we have negative 5 squared, which is 25, plus 2 squared, which is 4. So that gives us a square root of 29. So we're comparing the length of CB and DA. So we established that CB is the square root of 29. Now let's look at DA. So the x-coordinates, the difference of the x-coordinates are minus 3 minus 2 squared plus 2 minus 0 squared. So here we're going to end up with, so we're going to have negative 3 minus 2 is going to be negative 5 squared, which is going to be 25, plus 2 squared, which is going to be 4. So once again, we have the square root of 29. So using the distance formula was one way to prove that these two sides are congruent. We also know that these sides have to be parallel. So let's prove that C and B is parallel to D and A. So we want to do that by finding the slope. So to find the slope, we do the change in y over the change in x. So we look at CB. So CB starts up here with 6 minus 4 over negative 2 minus 3. So we have 2 over 5, and that's negative. So let's find the slope of, DA. So for DA1, use the same equation, y2 minus y1 over x2 minus x1. So the y2 would be the a's, so that would be 0. minus 2. And we're basing this off of a. So 2 minus a minus 3. And that leaves us with negative 2 over 5. So these sides are congruent and they are parallel. So that proves to us that these are the vertices of a parallelogram. In this problem, we're going to prove Theorem 6.6. We have our givens, and what we need to prove is that ABCD is a parallelogram. So in this example, we are given that line AB is congruent to line CD, and that line AD is congruent to line CB. This is given. Now, my angle here is that I want to prove that not only are CB and DA congruent, but they're also parallel as well. And I can do that if I prove that this diagonal creates two congruent triangles with corresponding parts that are congruent angles as well. So let's see how this develops. So I know that AC is congruent to AC. And we know that because of the reflexive property. Now I've proved that three sides are congruent. So I can prove that triangle ABC is congruent to triangle ADC. And here we use side, side, side. Now that I've proved that these triangles are congruent, I can say that angle DAC, which is this one, has to be congruent to this angle, which is angle ACB. Now I also know that this angle right here is congruent to this angle as well. So I know that angle ADC is congruent to angle CAB. And the reason I know this is because of the corresponding parts of congruent triangles are congruent. So now that I know that those angles are congruent, I can say something about line CB and line DA. And what's that? That is that these lines have to be parallel because of the alternate interior angle converse. I know that these given angles are congruent, so I can make a conclusion about the sides. So the sides, I want to say that side CB is parallel to side DA. And that side CD has to be parallel with side BA. So now I've proven that not only is CB congruent to DA, well I was given that, but I've proven that these need to be parallel. So my sixth statement, which I write up here, is that ABCD is a parallelogram. And the reason is that is the definition of a parallelogram. Okay? So once again, we knew that AB and CD were congruent and that AD and CB were congruent. What we needed to prove was that they were parallel to each other. And once we did that, we satisfied all the requirements for a quadrilateral to be a parallelogram. Okay, well, we're going to end there for today. Once again, thank you, and I'll see you in the next video.